So now I can do the summation of forces apply the second law. As usual, we might think about starting with the y component. So tell me about the acceleration of this car in the y direction. It ain't 0. And here's the first case of why I harangued you about don't ever, 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 ever write sum of the forces equals 0. Because you will do it for cases where it ain't. And it ain't 0 here. Think of this acceleration vector. We just sort of draw it over here. This is the acceleration vector, a sub c. That's not pointing in the x direction or the y direction, is it? In fact, it has a component this way, and it has a component that way, doesn't it? So there is both an x and a y component to that acceleration. Let's think about it a little bit. Let me just draw it up here. So we would resolve that into components. What's that angle? Yeah, it's going to be the angle theta. Oh, and what's the magnitude of the hypotenuse? B squared over r. Okay. So now you got what you need. So what's ma sub y? Well, there's m, but what's a sub y?
B squared over r.
So it's b squared over r sine theta. Okay, this is one of the reasons why you never, never, never jump to the conclusion that an acceleration is 0. You always ask the question. So now we do the other side. So do we have a y component for this force? Yeah, what is it? mg cosine theta. Plus or minus? So minus mg cosine theta. Do we have a y component for either one of these forces? And does it matter which one we pick? In both cases, it's the normal, isn't it? And that must be, according to this, m v squared over r sine theta. So let me solve for the normal, since I know that that's something I'm going to need eventually. So this is going to be m v squared sine theta over r plus mg cosine theta. So let me ask you a question. Is the magnitude of the normal component of the force that the implied roadway exerts on the car greater than